f of x equals this integral from the square root of x to 2x arc tangent t dt. Okay, perfect. So in this case, we still have to break it up, and as we know, it doesn't matter where. You can write 0 if that's what you want. You can write 10 if that's what you want, as long as you write 10 here as well. And this has to be reversed, the limits of integration. And now uppercase f prime. When I differentiate this, I get minus r tangent of the square root of x times the inner function prime. And then plus, I differentiate this piece, r tangent to x times the inner function prime. Make sure you are not attempting to simplify anything. This is the argument of this function, which cannot be simplified with anything. The same thing here. Good. Any questions? Good pick. Anything here? Okay, so I would like to talk about indefinite integrals now. We're not going to be able to finish this, so I'm hoping that this is very simple. It's not going to be difficult at all, the substitution rule for definite and indefinite integrals. But I would like to start the indefinite integrals today and this next time, and there is no more new material after this. This is it. This is the last section. So let's talk about indefinite integrals and practice. So 5.4, indefinite integrals. So we know that there are two types of integrals. And we talked in detail about one of them. That's the definite, which is the integral from, as an example, 0 to 2 from x squared dx. That's an example. What will be the indefinite? And always remember, we got this as x cubed over 3, so this was 8/3. We did that last time. Okay, what about the indefinite? And also, let me make sure I cannot check. So make sure you do it slowly, carefully, because there is no way you can check this number. Also, the definite integral is always a number. The result is always a number, and I cannot check it. What about the indefinite? The indefinite integral does not have limits of integration. So for example, I could have something like this. The antiderivative, we know it's x cubed over 3 plus a constant c, right? So this is the most general antiderivative. It's a family of functions. Most general antiderivative. It's a family of functions. Infinitely many functions are here. Infinitely many, because c is anything between negative infinity and infinity. So this derivative is x squared. A family of functions having the same derivative. So what I would like to do now is using the fundamental theorem of calculus is only for definite integrals, but just work on some examples using the symbol, the integral symbol for the indefinite integrals, and find the most general antiderivative. Now, here, I can check. So for indefinite integrals, I can always check. How? By differentiating. How will I check my answer here? I will differentiate the left-hand side, and I will differentiate the right-hand side. When I differentiate the right-hand side, I get x squared. When I differentiate the left-hand side, this and this are canceled by this. symbol. So I have x squared. So x squared equals x squared. With definite, I can only hope. The number, there is no way I can check. I can do it twice or 3 times to make sure I get the same answer, if that's what you want, but I cannot really check this answer. Yes, you have the calculator, but in general, that's what I'm saying. Yes, you can plug in the calculator. But here, I don't need anyone to tell me if this is correct. I will differentiate both sides, and I'll show that this is correct, because the derivative of this is x squared. The derivative, as we learned from Fundamental Theorem of Calculus Part 1, the derivative of an integral is the function. So, and there is one application here, the total change theorem. But I would like to practice, and if we can talk about it, but if not, we can. So it's the net change theorem. So we talked about indefinite integrals, and we're going to practice now, and this may have to wait till Wednesday, together with these. Okay. Verify, we differentiate both sides, we have to get the same thing. Guaranteed. So we can do those. Find the general indefinite integral. Anything you like from 5 to 24.
Can we do 22?
Yes, we'll start with 22. Perfect example. These are all the same thing, but they are definite integrals, and we discussed all these. So they're just throwing back at us other examples, but this is what we already discussed. So let's start with 22. Here it is. I had a cup of water. Yeah, I got it. Good. Which page am I on? I'm on 14. So 22. The integral from secant t plus tangent t dt. Perfect example. There is no technique here. Basically, is the integral from secant times secant dt plus secant times tangent. Which function prime is secant squared?
Tangent.
Very good. Plus, which function prime is secant tangent?
Oops. No, I can't remember.
Plus a constancy. That's it. Secant prime is secant tangent. Tangent prime is secant squared. And this is it. Can I check? Sure. If you differentiate this and differentiate that, you'll get the same function on both sides. Guaranteed. Okay, more examples. Good pick. 22 was a good pick.
Can you do number 18?
18 it is. Very good. Awesome. So in 18, we have the integral from 2 plus 3 to the x dx. Perfect. Very good pick. Thank you so much for picking that. So let's analyze this for a moment before we come back. Remember when we differentiated e to the x? We got e to the x. But when we differentiated a to x, anyone remembers how much was this?
Is it x to ln?
So it's a to the x times natural log a. Here, I should write natural log e, but I don't. Why? Because it's 1. Correct. So now, when we want to integrate, so this was be 3 to the x, prime will be 3 to the x times natural log 3. In order to determine this, I have to divide both sides by natural log 3. Right? So, which function prime is 2? That's easy. But plus, which function prime is 3 to the x? Is 3 to the x over natural log 3 plus a constant c. How come? because when I differentiate this, I get 3 to the x times natural log 3, which simplifies natural log 3, and that's how I get this back. Perfect pick. Thank you so much for picking that. I really appreciate it. So keep in mind these properties or these rules. So can I differentiate? Yes. 2x prime is 2. C prime is 0, gone. But when I differentiate this, I get 3 to the x times natural log 3 with the denominator, which is a constant. And that's how I get 3 to the x. Good, good. Okay, let's take a look. Anything else? Anything else that catches your eye? What's all this? This is the integral of 1. What's going on here? So it's just x plus a constant c. I don't know if they really meant that, because you simplify, right? But what's the point? It's 1. I know we have like 2 minutes left, so I don't want to hold you, but I would like to choose one more.
Can you go down more?
Yes, yes.
Yeah, number 24.
24, very good. In 24, if we don't remember what sine 2x equals to, we are in trouble. So anyone remembers what sine 2x equals to? It's a trig identity, a very important trig identity of sine over the double angle. Please, I'm begging you, do not do this. I've seen it. And the student says, oh, this is the integral of 2 dx. So please, 2x is the argument of the sine at the top, and x is the argument of the sine in the denominator. Anyone remembers sine 2x? 2 sine x cosine x. So the integral from sine 2x over sine x dx is the integral from all this at the top, 2 sine x cosine x over sine x dx. Yes, now you simplify because you simplify the same quantities and their factors. And this is 2, which function prime is cosine, is sine plus a constant c.